morning. I am Abhijit Dudnavkar, lecturer in Information Technology at SVKM Sri Bhagubhai Muftilal Polytechnic. In our course Optical Fiber Communication, we will demonstrate today how to measure numerical aperture using alignment model. This experiment, the outcome of this experiment lab is student will be able to make connections using analog transmitter and receiver and using alignment model, and they will be able to measure numerical aperture more specifically using this alignment model. Experimental setup. We will require power supply, dual power supply, single power supply, then analog transmitter, analog receiver, input as a function generator, and output at our CRO. Also, we will require an alignment model. Connections. First, we will connect power supply plus minus 9 volt to the receiver and plus 9 volts to a transmitter circuit. Then we will connect 1 meter fiber into this alignment model and another 1 meter fiber from this alignment model to the receiver. Input is connected from this function generator, where we set function generator initially at 1 kHz 2 volt peak to peak. We set this CRO where channel 1 is showing input which we applied, and channel 2 is showing what output we received after 2 meter fiber. Let me explain you what is alignment model first. This alignment model has two moving parts. One, this part is movable in laterally like this, and this part is also able to move end-gaply. That means it can move away from this model. So we have two model. This square model can move laterally like this with the axis of the fiber, and it can also move away from the end of the tip. By default, the distance between these two model is 3 mm, that is default distance. Then we have a second model which is an angular model. We can make an angle using this scale. So this model is movable like the angle, like this way, right? We can move. Initially we can set it to colliding or align with the axis of this fiber and this fiber, so it is marking at 0 degree. Similarly, we have this two screw. By means of that we can move our model laterally or our model end-gaply. To measure numerical aperture, we are using this model where we are going to move our fiber laterally from its center point towards left or right. In both the way, when we move from left to right, coupling of the optical power from this transmitter will going to be get reduced as I will move this model either left or right, and my output will start decreasing. That I will just let you demonstrate. This is my output. Output is shown here. You can see. I will just make it arranged like this way. Okay. Now let me show you how output is going to change. If I move 0.25 mm lateral displacement, right, I can able to measure this input. Then let me increase 0.5, 0.75 mm, 1 mm. So my lateral displacement now, this model is moved almost 1 mm. My output is still in measurable range. Let me change these values little more. Now you can see it is gradually decreasing. if you see at this certain value, it cannot be measurable. It's almost coming noise. That means the coupling which was previously available here, that is now mismatched completely, and now I reach to the end circumference of the second fiber, and that's why coupling is not possible. So what actually meaning is that this lateral displacement actually tells you that this is your radius of the cone which is being developed when light is being propagated, right? So what I will do, I will measure and I will record it into table, and that we can proceed like they will. Let me set it to its default value. So I will set this into middle first, right? Then I will take I will make a table. This I will show you. Okay, in this table I have initially took for D default value 3 mm, that is my default value D equal to 3 mm. For this D equal to 3 mm, currently my lateral displacement is 0 mm. Now for that 0 mm, my output is about 1 division, 2 division into 50 millivolts. So 2 divisions multiplied by 50 millivolts, that is 0.1 volt, that is 100 millivolt, is my output, V output, right? Now what I will do, I will increase this lateral displacement to reach to the circumference of the second fiber. So I will increase in the steps of 0.25 mm. So initially I will make it 0.25 mm and I will try to measure it, and I am able to observe the output is not changed, it's remain that same value. For 0.25 my output is 1 millivolt, 100 millivolt, that is 0.1 volt. Again I will increase to 0.5 lateral displacement, 0.5 mm lateral displacement, my output is still 0.1 volt. Again I will increase, I will make it 0.75 mm. Now output is still that value, 0.1 volt. Then I will increase to 1 millimeter distance. Now little difference is there, and it's almost about 1.8 into 50 millivolt. So that it comes to 0.09 or 90 millivolts. So my output decreased about 10 millivolts. Let's see, I will increase it to 1.25 millimeter lateral displacement, and now my output is still that value, 90 millivolt for 1.25. Then I will increase to 0.5. Now you can able to see output is decreased almost half value, and now my output is about 1.4 into 50 millivolts, which comes to about 70 millivolts. Then I'll increase to 0.15, and now you can measure, it's almost in the range of, we reach almost at the circumference of the second fiber. So from this we can conclude some way that our fiber, I mean to say the radius from the center of this fiber axis to the circumference is about 1.5 millimeter. So I can take this R value, R is equal to 1.5 millimeter, because my output is suddenly decreased here, because I got in a mismatch here. Previously it was maximum at when the both fiber were exactly having in the same alignment, their axis was coinciding to each other. But now there is a lateral displacement of 1.5 millimeter, which is causing, you can see this, both the module, if you take vertically, the module, you can see they are laterally displaced by 1.5 mm. Now this 1.5 mm makes the cone going out of the vision of this another fiber, and so that the coupling is becoming lesser and still we have a 3 mm gap. You can see my pencil tip here. This 3 mm gap is there. This is default gap in this model, and my model, if you see, the notch is available here, a white color notch you can see, and there is a scale also on this model which showing me I have moved the screw about 1.5 millimeter, and that is my lateral displacement. And that lateral displacement is set to be a radius, and this d is a distance. So using this d value and r value, we can use our formula. That is, our formula was sine of phi by 2, this one. This r we have just calculated. For this d, that is d we have taken in this account, that d is equal to 3 millimeter. D is 3 millimeter, and formula is r divided by root r square plus d square. Now if we put these all values, 1.5 millimeter divided by 1.5 whole square plus d is 3 millimeter square, whole thing in root. If we calculate it, just pop. This is 1.5, then we calculated this value and it comes to 11.25, and if we solve this, this comes to 1.5 divided by 3.54. Now if we calculate this 1.5 divided by 3.54, our value of Na comes to 0.42. That is, our fiber has numerical aperture of 0.42. Now if we take a sine inverse of this 0.42, it comes around 27 degree. So what we can say, by using this alignment model, we can calculate, we can vary this value, vary the lateral displacement, vary this d value. By using this d and r value, we have come to know that our Na is 0.42, and if we take a sine inverse of this 0.42, that comes around 27 degree. So acceptance cone for this fiber is 27 degree. Na for this fiber is 0.42. Thank you.